Hey guys, Dr. J here. So today we're going to do part two, part two of data collection for our acceleration lab. So this will be the last data set that we collect for our acceleration lab, but this is actually going to be a two-part assignment because we're going to have to do quite a bit. So what's going to be due today will be lecture notes and lab procedure notes on this video here, and then you're going to turn in next time your second spreadsheet, which is going to have a good amount of things going on. So let's go ahead and get started and we'll look at what we're doing. Okay, so this, let me go ahead and zoom in a little bit. This is a copy of like the average data or the average, the average result really that we got from our first day of data collection. Okay, so for most people, for the low block trial, and I'm gonna pause the recording and go get a block. Okay, so I'm back in the lab and I'll just be over here so that we can have a relationship between what's on the spreadsheet, and we can very easily visualize the terms on this, the relationship between the terms on the spreadsheet and then the data that we collected. So our first trial was this low block trial. Okay, low block trial. Well, that was with the sort of low position for putting the ramp on the block. The second trial that we performed was the high block trial. So you flip this block upright and you put the ramp right there. Okay. And then the last trial, of course, was on the table that was used as a ramp, right? So the table that's right over there, okay? That table being used as a ramp. All right, so those were the three trials we performed. And when we performed those trials, on average, we got data that looked like these data that we're seeing here. Okay, so what are we going to do with these data? Well, scientists typically collect data so that they can understand a larger picture. So they do a series of experiments, right? And experiments are limited. So they just tell us about a few things, right? The experiments tell us about how a golf ball travels down this ramp or how the golf ball travels down a table. But what's important about scientific experiments is that we can take the information that we learn from those experiments and use that information to understand other scenarios elsewhere in the world, right? And so it turns out that gravity makes this golf ball fall. And ultimately, in this lab, we're understanding the effects of gravity to cause acceleration, but we're also learning about acceleration and we're learning about velocity. So through these experiments, we want to develop a broader understanding of the physical world. Okay, so that sounds like a lofty ambition. Let's go ahead and get into the nitty gritty of that, and we'll continue our discussion of the way that scientists use their experiments and their results to better understand the world around them another time or as we continue through the course. So what are we going to do today specifically? So the first thing we're going to do is we're going to try to understand the relationship between height and average velocity. So we have some really nice data here. Let's go ahead and turn them into a graph. So the first thing I do is I select these data, and then I go to Insert, Chart. Okay, and the first thing it gives me is this chart, and what you want is a scatter chart, right? And so you want to make sure you've got a scatter chart. Okay, scatter chart, you might have to scroll down to go to scatter in order to find that chart, but that's what you want. You want a scatter chart. And this is a pretty good looking graph, okay? The next thing that I want to do is I want to go to, let me find it. Is it in series? Yeah, I go to series and I add trend line. And the type of trend line that's going to work best for us is a power series trend line. And then what I want to show as the label is the equation for the trend line, okay? So the equation I get is 3.24 times x to the power of 0.58. Okay, that's a lot. Let's back up. So I'm going to delete this entire chart. I'll leave it up here for a second like this so you can see. I'm going to delete this entire chart, and then I'm going to redo that whole process from the beginning so you can just sort of more slowly see it again. Okay, so I've got my data selected. And you should probably write these instructions in your notes. You go, or you can follow along with your own spreadsheet, which would be even better. You go to Insert, Chart. You want to make sure you get a scatter chart. If a scatter chart doesn't pop up for you, under Chart Type, click, and then go to Scatter. Now, the next thing you want to do is you want to, I don't know why, yeah, you want to customize. So click on, so this is setup. You want to click on Customize and go to Legend, which is a strange thing to click on for this purpose. Or no, go to Series. There we go, Series. And you want to click on Trend Line. What Trend Line does is it tries to fit a mathematical model or a mathematical formula to your data. So what that means is you'll be able to take your data and apply them to other situations, other heights. You'll be able to make predictions for other heights that you didn't measure. So for instance, in this case, I have one height at roughly 0.22 centimeters. I've got another height of 0.73 centimeters. Well, what if I wanted to know the average velocity if I released the ball at 0.22 meters, 0.73 meters? What if I wanted to know the velocity if I released the ball at 0.4 meters, right? So if I wanted to know the velocity at 0.4 meters, I'd have to understand the mathematical relationship among these points. And this trend line will allow me to do that. It'll provide that kind of a relationship. So I click on trend line, then I go not to exponential, but I go to power series. And you can see that I get a very good fit there. And for those who are interested, this little R squared value, if I click there, that shows the degree of fit, okay, or the confidence that I can have in this fit. And 0.994 is very high because it's very close to 1. So this R squared value that's almost equal to 1 shows me that this formula fits my data quite well, okay? So for these data, this formula is fantastic. So I'll get rid of that for now because we don't really need it long term. But what I am going to show is, it's under series, I guess. Under series, under label, I go to use equation. So now I can see the equation that the Google Sheet is using to produce this curve, this function, okay? So this equation is that, or this equation states that the average velocity is equal to the number 3.24 times, okay, whatever height value we plug in meters raised to the power of 0.58, all right? So that's the mathematical relationship that I'm getting for my data. When you go through this process for your data, you'll get a slightly different mathematical relationship. What I want you to do now is to go ahead and go through your data and find that mathematical relationship, okay? Please go ahead and pause the video and go through the steps that I've just gone through. Okay, so now I'm back at my desk and we're going to have a little bit of a lecture, all right? So what I want you to do is I want you to make sure that you copy down this equation, okay? Copy that down somewhere. You're going to need it in your notes. I'm going to need this equation in my notes. I'm going to copy it down on a little piece of paper for myself right now. Okay, and now let's go ahead and take a look at the whiteboard. So we'll talk about what we're going to do next. All right, so here we go. So just for record, and I just put this off to the side for myself, right? My velocity, I wrote this down. I'm going to erase this quickly. My velocity equals 3.24 times height, which Google Sheets treats as x, to the power of 0.58. Okay, that's my little equation. I'm going to go ahead and clear that out for now. I'll use it again later. All right. So today we're going to be studying a concept of, we're going to be studying two really important concepts within the context of our lab. So we're going to be studying interpolation. So this is the acceleration lab. Okay, and we're thinking about interpolation versus extrapolation. Okay. All right. So, okay, what in the world are these things? So today, remember, you're going to be turning in your notes. Okay, you're going to be turning in your lecture notes. So let's go ahead and define some terms and get some good notes that we can turn in. So the first thing that we need to understand regarding what we're doing today is this concept of interpolation. And I'll go ahead and get a definition on the board so the video doesn't get too long. Okay, so I'll define interpolation as making a prediction within the boundaries of known or measured data. Okay, so like, here's an example, right? If I've got a graph and I've got these points, and I'll go ahead and make this look like the graph that we're graphing, right? If I want to interpolate, okay, so interpolation would be predicting here, or predicting here, or predicting here. Because what I've already got are measurements for these particular X values, here, 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 and here. So if I want to, I can interpolate, okay, here to predict that this X value will give me a Y value probably about there. Or I could say that this X value would give me a Y value probably about there, okay? Or maybe this X value will give me a Y value probably about there, okay? That's interpolation. I'm interpolating within the boundaries of my measured data, right? I'm not going any farther than this last measured X value, okay? I'm inside the boundaries. I'm within the boundaries of what I already know and what I've already measured, okay? Extrapolation is different. So extrapolation, I'll go ahead and pause and get the whole definition up for you. Okay, so extrapolation means, and I'll use yellow for this guy, it means predicting beyond the boundaries, beyond or outside of the boundaries of the known or measured data, okay? So with these data, if I want to make an extrapolation, I can like extend out my x-axis and I can say, okay, well, maybe I'm interested in this point over here, right? Which is outside of my measured data. And I might predict that the average velocity would be right there, or the corresponding Y value would be right there for this particular value of X. It would give me this value of Y, right? This value of Y over here, okay? So that's extrapolation. So interpolation, making predictions within the boundaries of our data, right? And our data that are measured are represented by these blue dots. Extrapolation allows us to make predictions outside of the boundaries of our data, okay? But we have to understand as scientists that extrapolation is really tricky business. So let's talk a little bit about that right now. Okay, so the title of this next panel is Predicting Prudently. And what does prudently mean? So prudently, right, means responsibly, okay? Or carefully, right? So this is like carefully. Whoops. Let me get that whiteboard back up. Carefully. / responsibly. Okay, predicting carefully and responsibly. All right, that's what it means. So what should we know in order to do that? So interpolation is generally a reasonable or prudent or accurate process. Okay, extrapolation is riskier. Extrapolation is riskier especially when the boundaries, or sorry, when when performed on values that far exceed the boundaries of known / measured data. Okay, known / measured data. So I'm going to go ahead and pause. Okay, so now we have our equation. And in my case, right, my data allowed me to determine this formula. Velocity equals 3.24 times height to the power of 0.58. Okay, and velocity, this velocity is in meters per second. Okay, meters per second. All right, so my formula allows me to estimate that velocity using this formula. However, this formula, or this relationship, this formula / relationship, was established from height measurements between 0.0 meters and 0.00 meters and 0.73 meters. Okay, 0.00 meters and 0.73 meters. Okay, how accurately will this type of relationship interpolate, and extrapolate. Okay, we'll have to discuss that next time. Okay, next time. But I'm not going to leave you totally hanging. All right, so go ahead and get this into your notes, but I'm not going to leave you totally hanging. I want you to see where we're going with this. So I'm going to go ahead and stop the screen share here. So we like to do fun things in science class, or at least as fun as we can do with the budget and the time and the safety requirements that we have right in place. And that's fine because we can still have a lot of fun, right? So the highest height that we measured in the lab here in the room was 4.9 meters, right? So the height of one of these desks, okay, one of these desks is starting out 4.9 meters. 0.73 meters, 0.73 meters, which is the height of one of these desks, okay? But it turns out, and here's where that number comes from, it turns out that we can predict, right, velocity using that same formula from a much greater height. So here I am out on the balcony, and it turns out that this balcony here, okay, and I'm gonna go ahead and put my hand on the railing. This balcony railing here, this guy where I'm bouncing the golf ball, this guy is 4.9 meters above the ground, right? There's the ground, okay? How you doing? So we can go ahead and drop a golf ball from this railing, and we can use our formula, okay, to predict how quickly that golf ball should be going or how fast it should be going when it reaches the bottom. Separately, we can use the known height of that balcony to measure the known height of that balcony and our stopwatch to actually measure that velocity or calculate that velocity, okay, from distance and time data, okay? But those are things that we will be doing and discussing, among other things, next time.